Hello professors, my name is Muhammad Umair Munir and I am a student of Power Electronics Lab, and I'm doing my Masters under the supervision of Professor Park Jong-Hoo. My thesis title is Low Cost Single-Ended ISM Band Frequency DC-DC Converter with very high step-up voltage gain. And actually I will start my presentation from the previous work, what we have done previously in the first defense. So previously I have talked about the motivation and the problem statement. Due to the rapid advancements in power electronics, switching power systems have undergone significant enhancements, becoming more compact, efficient and cost effective. Industry is actively finding the balance between size, cost and performance by finding the better design topologies and by omitting the intermediary stages. A DC-DC converter setup is shown in figure 1. These DC-DC converters are limited by their conversion ratios when applied with a very low input voltage and are unable to step up the DC link, the voltage level to the DC link voltage level. So therefore these DC-DC converters have often relied on battery banks source with voltage of 24 to 48 to facilitate stepping up to the required DC link level voltage. So however, to make these 24 voltage or 48 voltage, we need to connect the battery cells in series, which cause some potential issues like the thermal runaway, cell degradation, incomplete charging, discharging, suboptimal energy or utilization. Balancing circuits, therefore, to get rid of these problems and to solve these problems, balancing circuits are used to overcome these issues. However, they also come with some potential issues like energy loss, complexity of system, increased cost, bulkiness of system, reduction in overall efficiency. To overcome all these issues, there is a need for a converter which can directly step up the voltage of a single lithium-ion voltage cell to the level of DC link voltage. Additionally, for the reduction of the size and increase the energy density, higher frequency operation would be beneficial. And apart from these low voltage sources, I want to highlight a point that these days a lot of companies, they are actually recycling the aged batteries and the aged battery cells, and then they are sending it again to the companies to use it again. But the problem is these aged battery cells, companies are afraid to use them in series connections because of the huge unbalance between the voltages. So if we have a converter that can step up the voltage of a single lithium-ion cell from the single lithium-ion cell to the level of DC link voltage, then it would be very beneficial in terms of the recycling of the battery. So we can use these aged cells in these converters. Here is the literature review. Numerous high voltage step-up converters have been proposed in existing literature, each distinguished by its voltage boosting capabilities, component count, efficiency, physical size and operational frequency. So the problem of these converters is a high number of components. Some of these converters suffer from the problem of inrush current and hard switching. Additionally, switch stress can be higher in some cases and voltage gain is not up to the mark. Therefore, there is a need for a converter that can have a very high step-up voltage gain. So the objectives of the proposed converter is a very high voltage step-up ratio of more than 100 times and ISM band switching frequency operation up to 6.78 MHz for high energy density, which is approved band for power purposes, which means that there will be no need to get the extra license to operate the converters. Soft switching of the MOSFET, less device stress, better efficiency, smaller size and less number of components, etc. The proposed proposed circuit is shown in figure 3, and it consists of a tapped inductor, a single switch, 2 diodes and a flying capacitor and load resistor parallel with the capacitor. The tapped inductor is a coupled tapped inductor. The relationship between L1 and L2 can be determined by this magnetic element equation. This component enables the high input-output conversion ratio while reducing the voltage stress of the MOSFET and helps in the soft switching operation of the MOSFET. And apart from these benefits of the tapped inductor, I just want to highlight one point that previously I have mentioned that these tapped inductors sometimes suffer from the problem of the leakage inductance, which cause the high voltage spikes on the switches. However, in the proposed topology, the switch stress, because since the switching frequency is very high, the switch stress, the switch parallel capacitor can mitigate these spikes, so there will be no need of extra circuitry to mitigate these spikes. And these are some important ideal waveforms in the DCM mode. And here are the modes of operation. And in the first mode of operation, the S1 is on, and the inductor L1 is charging, and also the capacitor C1 is charging to the D1, and the load is fed by the C2. And in second mode of operation, the capacitor C1 is already charged to the value of this equation, but the inductor is still charging, inductor L1, and the load is fed by the output capacitor. In the mode 3, the switch is off, D1 is reversed by, D2 is forward biased, and L1 is no longer receives energy from input source. Voltage across the switch starts to rise. Inductor current drops abruptly because of the current flow in both the inductors L1 and L2, and its peaks can be calculated by using this equation. Since the D2 is forward biased, L1 and L2 are connected to load, and the pump the charge the stored energy through C1 to the load. And in the fourth mode, since it's a DCM converter, so all the semiconductor devices are off in this mode, and inductor does not have any energy to provide to the load. Load is fed by the capacitor C2. And here are actually the gain equations that can be used to directly calculate the gain of the converter and to design some of the converter elements. Like to find the duty ratio, we can use the equation number 9, and to find the L1 value, we can use the equation number 8, etc. And it can be seen that in figure 10, the voltage gain of the proposed converter is increasing as the value of the tau is decreasing, where tau actually is a time constant, which is a combination of L1 over T over R. And if we decrease the value of tau, we can successfully get a very high voltage gain. And the voltage gain of this converter is actually linear with the duty ratio. So it is easy to design the control of the proposed converter. And figure 11 shows the non-ideal case voltage gain. It can be seen that the voltage gain, even if we have a very high RDS on of the switch or the resistance of the tapped inductor, still we can achieve the 100 times voltage gain easily. And this slide actually shows the component stress. The switch voltage stress can be found by using this equation. In figure 12, it can be seen that by using the tapped inductor, even if the turn ratio is 1, our switch stress is half of the voltage gain, and which is one of the major benefits of using this tapped inductor, allowing us to use the low voltage, low cost switches. And the switch stress can easily be controlled by increasing the turn ratio. And converter design specs, as discussed in previous sections, proposed converter is meant to be used to step up of a single lithium ion cell voltages. The nominal voltage of this lithium ion cell is in the range of 3.7 to 4.2 voltage in most of the cases. Therefore, the 4 voltage is selected as a input to the converter, which will be scaled up to the DC link level. And these are the specs of the converter. The output power will be 32 watt, and the switching frequency is 6.78 megahertz, and in output voltage will be 400 volts. So previously we have used a demo board just to see if our proposed circuit is functioning correctly or not. So previously, because of the high loss in the switches, the switch had a very high RDS on. So because of that, we had a high loss in our system. So our efficiency was just 77%, and we were just able to test this circuit for 2 volt input to 200 volt output. Therefore, there was a need to design a PCB circuit, and also we needed to optimize the inductor design. So these are some of the comments of the community members. That one of the comments was is the inductor optimized? So we actually gave the optimization process for the inductor, and we have already optimized our inductor. And also the other comments are already taken into account. So since we are operating our converter at 6.78 megahertz, we need a very small value of the primary inductance. Therefore, to design this very small value of primary inductance, which is in the range of maybe 12 to 15 nanohenry, it will be hard to design by using the conventional methods. So there is a need for the design guidelines. So we have actually presented a inductor design flowchart. So this flowchart can be taken as a guide in order to design the inductor very effectively for this much high frequency. in terms of the inductance value and in terms of the loss. So first of all, we need to have the converter design specs which are already described in the previous slides, and then we can find the primary inductance value by using the equation 60. And also, once we have find the value of the L1, then we have to actually design it physically. So to design physically, we need to use the equation number 17, and in this, according to this equation, the inner radius is very dominant factor in our case. So we can first choose the inner radius which will be actually close to the our inductance value. So we can actually tune the value of R to find the value nearby value of our desired inductance value, and then we can change the values of the thickness and the width of the tapped inductor, or the primary of the tapped inductor, which will help us to reduce the resistance of the inductor. So after the designing it mathematically, we have to, the two-step FEM verification is actually suggested. In the first step, only the primary inductance should be designed according to the values that we have found from the equation number 17, and we need to find the resistance and the inductance values at the desired frequency. And once we have successfully find this value, then the second simulation should be done by placing a secondary coil close to the primary coil, since this converter utilizes the tapped inductor. So we need to find the coupling coefficient, and also because there will be some proximity effect between the primary and secondary, which will affect our inductance and the resistance values. So to successfully design the resistors, we must do the second simulation as well. And after that, if our inductor design satisfy the design constraints like the inductance, the efficiency and gain, then we can implement it in the hardware, or fabricate it, or we can go back and tune the values. So actually this slide shows the effect for this equation number 17. If we change the value of R and also we change the value of the width, we can see that the R is the most dominant factor, and also the width is changing the resistance, but not inductance value, but not is not a dominant factor, but still there will be an optimum point which can be choose. And also it is dependent on the converter size constraints. If we have very tight constraints, still this guideline is actually very important, especially for the megahertz frequency range where the converter sizes are very small. And of course our main objective is to reduce the size of the magnetic elements. And also the equation shows in figure number 15 the effect of the thickness also shown. So it can be seen that by increasing the thickness, the inductance will be reduced, but we can choose an optimum point which will help us to have a better inductance value, our desired inductance value, and also the better resistance value, which will help to reduce the losses. So in our case, these are the selected values. And it can be seen that in figure 16 that the flux density is shown in figure number 16 at 6.78 megahertz for the designed inductor. And in the inner edges, the flux is is actually accumulated in the inner edges, which is because of the solenoid type the geometry, because in this geometry the flux is most of the time it is actually concentrated in the inner edges, and also there is some proximity effect from this edge to the adjacent edge, next adjacent edges. So this can be reduced by increasing the size of the coil, but of course it depends on the size constraints, and it will increase the inductance, so we need to tune this. And also the current density is shown in the figure number 17, and it can be seen that the inner edges has most of the current is in the inner edges, and also there are the 4 skins because of the rectangular section of the inductor. So this actually the inner edges has the most of the current density, which is because of the proximity effect from the adjacent edges. And it can be seen in the final values of the designed inductor at the 6.78 megahertz can be seen here in the table number 3, which are actually similar to the values that we have desired for. And now in this slide actually we are presenting the fabricated tapped inductors. We have fabricated 2 types of the inductors, type 1 and type 2. Type 1 inductor is a discrete wire wound inductor, and the type 2 is a semi PCB integrated inductor, primary is externally connected, while both turns of the secondary are integrated into PCB. And maybe in later design we can integrate both the primary and the secondary into the PCBs. So the hardware verification, the components are designed according to design specifications, and the values of all the new hardware values are presented in this table number 4. So, and the figure 21 shows the hardware setup. A PCB has been designed using a GAN switch, and figure 22 shows the optical image of PCB. The power density of the PCB is quite high, which is around 2.8 watt per cubic centimeter. And I want to mention one thing here, that in order to design this high frequency PCBs, the gate signal, it is actually very important to design the gate drive in a good way. Otherwise we will have the oscillations in the circuit, and which will make the wrong switching in the circuit. So in order to design the gate drive properly, we need to design a Kelvin source, so that the gate loop will not be affected by the power loop of the converter. So it is important to take these guidelines into account to successfully design the gate drive for this much high frequency. So in the figure 22, actually the first figure is for the type 1 inductor, and the second figure is for the type 2 inductor. And for hardware verification, figure 23 shows the hardware results of 4 volt input with the duty cycle of 0.69, and the resistance value output load value is 5 kilo ohm. It can be observed that the gain of is 100, which is achieved, which makes the output voltage as 401 volt. This verifies the effectiveness of the design converter. The output power is 32 watt. The efficiency with type 1 inductor is 84.81%, while the type 2 inductor is 85.1%. The switch voltage peak is just 138 volt, which is 3 times smaller than the output voltage. This shows the effectiveness of employing the tapped inductor, which helps to reduce the switch voltage stress while increasing the output voltage. A cheaper low voltage switch can be employed if we use the tapped inductor. And this figure 24 shows the soft switching verification of the converter. It can be observed that the circuit is soft switching, which means the switching losses are minimum. Switch capacitor helps to slow down the rise of the switch voltage at the off time, which helps to minimize the off time switching losses by minimizing the overlap between the switch current and the voltage. And efficiency curve, the figure 25, efficiency curve for the input voltage and regulation and output power regulation are shown in figure 25 to 26. In 25, the output power is kept as 32 watt and the output voltage is 400 watt, and the input voltage is vary from the 3.7 volt to 4.2 volt. It can be seen that the efficiency is increasing as the voltage increasing, which is because of the lower current in the primary side, which helps in the reduction of the conduction losses in both in the switch and the primary side of the tapped inductor. And also the figure 26 shows the output power regulation. It can be seen that for 4 voltage input, the maximum efficiency is achieved at the rated power of 32 watt, which is 85.1%, and for 4.2 voltage, which the maximum efficiency is 86%. The efficiency in 4.2 voltage is increased due to the reduction in the RMS current in the primary side of the tapped inductor and the switch. Figure 27 shows the loss breakdown of the converter for the rated power of 32 watt and the 4 volt input. The switch losses accounts for the 63% of the total losses, out of which the major losses are switch conduction losses, which can be further minimized by utilizing the low RDS on switches. Low RDS on switches, which dependent on the industry if we can find, and the inductor losses are 32%, while the diode losses and capacitor losses are only 3.5% and 1.5% respectively. This table 3 actually shows the comprehensive comparison with existing topologies. It can be seen that the proposed converter outperforms most of the existing topologies in the market. The switch stress, voltage stress is very low in the designed converter, proposed converter, and the voltage gain is actually 100 times. But we can see that all of the other converters, they have a very low voltage gain. So this shows the effectiveness of the proposed converter, and also The number of diodes used in the proposed converter only 2, and the capacitors only 2, but the other topologies have the high number of the diodes and the capacitors used. And also the proposed converter is soft switching. And some potential applications for the converter are the high voltage LED lights drivers, and as I mentioned earlier, the aged lithium ion cell voltage can be boosted up to the DC link level by using our proposed converter, because they are not preferred in series connection due to the extreme unbalance in the cell voltages. And also the unmanned vehicles, these days they require a 400 volt of 400 voltage as an input to drive some of the circuitries inside. So our proposed converter can easily be used to step up the single lithium ion cell voltage to the DC link level voltage. So as a conclusion, a novel ISM band frequency high step-up converter is proposed. Mathematical analysis and design guidelines are presented in details. Proposed converter can fulfill the high voltage step-up conversion requirements of various applications and can provide a gain of more than 100 times. Reduced component count and smaller size of converter. Soft switching of the MOSFET is achieved, which minimizes the switching losses. Simulation and hardware results prove that the employing a tapped inductor would help to lower down the switch stress and helps in the high voltage gain. Low voltage stress of the MOSFET allows the employment of low cost switch, which is one of the major advantages of the proposed topologies. And thank you very much for your time, attention and consideration.